Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I am Arif and I welcome you all to lecture number 14 on the subject of computer organization and assembly language programming. The title of today's session is Instruction Set Architecture Part 1. Well, today we will start with the overview of computer system. Then we will talk about its universality. We will talk about Alan Turing and his Turing machine and its practical implementation given by John von Neumann. Finally, I will touch upon the instruction set architecture of a computer system, and I will inshallah complete this topic in the next session. So let's start playing. Well, dear students, let me give a quick overview of computer system. First of all, the term memory refers to all the locations, rather all the collections of hardware devices that store data and instruction in a computer. Here only the main memory is shown, while we have talked about the cache and the secondary storage as well in our previous sessions. Anyways, from a programmer's perspective, all these memories have the same structure. A continuous array of cells of some fixed width, also called words, and each having a unique address. So a programmer can read and write any location of memory by specifying its address, and the word read or written at that location can be either a data item or maybe an instruction. And dear students, we have already designed different memory chips in our previous sessions that can perform all these tasks. Next comes the CPU. The first thing that we designed inside the CPU was the ALU chip that was capable of performing 18 different arithmetic and logic operations on two 16-bit values based on 6 control inputs. We also designed different register chips, which are small memory places inside the CPU that may hold data or maybe memory addresses or maybe instructions. And since these registers are located in the close proximity of the ALU, so they serve as high-speed local memory, allowing the processor to manipulate data and instructions quickly. Well, this setting enables the programmer to minimize the use of this memory access and thus speeding up the program execution. The one thing inside the CPU we have not touched upon yet is this control unit. The control unit actually tells the computer memory, ALU, and these IO devices as how to respond to the instructions that have been sent to the processor. And these instructions are of course machine instructions written in the processor's machine language. And remember, every processor has its own machine language. And a machine language is actually an agreed upon formalism designed to code low-level programs as a series of machine instructions. Using these instructions inside the memory, the programmer can command the CPU to fetch an instruction or data from the memory or maybe from the input device, perform arithmetic logic operations on that data, and finally store the result inside the memory maybe or maybe to be displayed on the output device. Moreover, data may need to be moved from one register to another and may need to test different Boolean conditions. Well, dear students, remember, although most people will never write programs directly in machine language, however, the study of low-level programming is a prerequisite to have a complete understanding of computer organization and architecture. And before we discuss as to how we can design the machine language of a specific processor, let me put the stage right by having a theoretical discussion about the universality of computer system. Dear students, most machines in the world do one thing. For example, uh, a washing machine washes clothes, and an air conditioner is used to control the temperature of a room. On the other hand, a computer, for example, a smartphone, can do lots and lots of things. For example, voice communication, word processing, playing games, using internet, watching videos, and so on. Well, the idea of universality, that is, same hardware can run many different software programs, was coined by Alan Turing in the 20th century, who gave the notion of a universal Turing machine. And the same idea was turned into practice by John von Neumann, who gave the notion of a stored program computer. Let me give you a brief description of these two notions. First of all, let us talk about the Turing machine. The Turing machine was invented in 1936 by Alan Turing, which is a simple device that can capture the notion of computability. And computability means what can or cannot be solved or computed on a computer. Well, a Turing machine is a mathematical model which consists of a state transition logic, a state register, a head, and an infinite length tape divided into cells on which the input is given. And the input can be data as well as instruction. It reads the input symbols pointed to by the head symbol according to the transition function, replaces this symbol with another symbol, change the register state, and moves this head to either left or right. On reaching the end of the string, if the register state is the accept state, the input string is accepted, otherwise it is rejected. So a Turing machine consists of a finite set of states, which is represented by Q, input alphabets, that are the allowed alphabets, the tape alphabets, which are the input symbols that can be written over here, the transition logic or function using which this head will move to either left or right by writing something over here and changing the state as well. One important state is the start state, represented by Q naught, and two other important states are accept state and reject state. So this is a basic idea that is written on this input tape, which subtracts two number and generates the result, that is 32. And of course, this program can be represented by a Turing machine, but let me give you a comparatively simpler example for better understanding. That is a Turing machine that checks an odd binary number. So this Turing machine that checks an odd binary number will have these states Q0, Q1, QA, QAccept and reject. The input alphabets are 0 and 1 because the string will only contain either of these two symbols. And the tape alphabets can be 0, 1 as well as space. This is the transition function. I will describe this in a bit of time. The start state is Q naught, the accept and reject state are QA and QR. This is the transition table, and this is the graphical representation of this transition table, also called the state diagram. Before proceeding, let me describe this a little bit for better understanding. This is the state Q naught, this is the state Q1, this is QR, and this is QA. This row of transition table tells you that if at state Q0 you get an input of 0, you stay at Q0, you write down a 0 on the tape and you move the head to right. So at state Q0, if the input is 0, we replace it with 0 and we move the head to right and stay on the same state. If at state q naught we get a space, we replace it with a space, move the head to the left, and change the state of the state register to q1. So you can easily map this transition table to this state diagram. Let me move on to an example. Let's suppose that we have this Turing machine and the input string is 1011, and we want this Turing machine to decide whether this is an odd number or it is an even number. If this is an odd number, this Turing machine should finally reach to QA, and if this is an even number, this Turing machine will finally reach at QR. And it is very simple to understand that since the least significant bit is 1, so this is an odd number. However, let me check it step by step. Right now the current state is Q0, head is pointing at this location of the tape and the symbol is 1. So at Q0, if we read 1, we replace it with 1, stays at Q0 and move the head to the right. So we move the head to the right. The current state is Q0, the head is reading 0. At Q0, if we read 0, we replace it with 0, stays at Q0 and moves the head to the right. Since we are at Q0 and we are reading 1, so we stays at Q0 again. And over here again, since the current state is Q0, the symbol under the head is 1, so we stay at Q0 and move the head to the right. Okay, now this is interesting. The current state is Q0, the head is reading a space on the tape. The current state is Q0, we are reading space. So we will write a space over there, move the head to the left, and the state will be changed to Q1. So this will be changed to Q1 and our head will move to left. So now we are at state Q1 and the symbol under the head is 1. So we read 1, we replace it with 1 and move the symbol to the right. And there we go. And the state is QA. So since the final state is QA, so that means this string is accepted by this TM. So this string is an odd binary number. Let me show you another example, and that is of an even number 1010. The same state diagram, we keep reading and keep staying at Q0, keep staying at Q0, and once we reach over here, the current state is Q0, the symbol is space, so we move on to state Q1 by writing a space over there and moving the head to the left. So the head will move left and we will have Q1 over here. So now the current state is Q1, the symbol is 0, so we read 0, write 0 over there, move to right, the head moves to the right position in the right cell and the state will be QR. So this string has been rejected by this TM. So that means this is not an odd number. Anyways, so dear students, this is just an overview of this Turing machine. I am sure in the upcoming courses like Theory of Automata, you will be going into the details of this and some other machines which will identify different strings and move on to the accept and the reject states. If you have not understood it, I will request you to please rewind this part of the video and watch it again. Just remember, this is a theoretical model that was practically implemented by von Neumann. And this is the von Neumann architecture, and that describes the architecture of an electronic digital computer having these components. that we have already discussed, a processing unit that controls the ALU and the registers, a control unit that contains the instruction register and the program counter as well, that decides which instruction to execute next. And we have the memory unit that stores the data as well as the instructions, some I/O mechanisms and I/O devices, and maybe external mass storage. So this is the overall architecture of von Neumann architecture that that you see in everyday's computer these days. Okay. So the main idea in this architecture is the stored program concept. That there is one memory, and inside this memory there is a portion that contains the program instructions, and there is a portion that contains the data, on which these instructions are going to operate. And this is how the same hardware can run many different software programs. So this is the same hardware. We have a different program over here. So the same hardware will be doing something else. And if we load a different program over here, the same hardware will be doing something else. Well, dear students, as I have already said, that a machine language is an agreed upon formalism designed to code low-level programs as a series of machine instructions. The control unit actually is the one that need to know which is the machine instruction actually which it needs to execute. And we all know that there is a special register called the program counter that contains the memory address of the next instruction to be executed. And let's suppose that the program counter contains 1. So this is the next instruction which need to be executed, a 16-bit instruction which the control unit need to execute. So this machine instruction is fetched by the control unit in some special register over here, normally called the instruction register. And now the $100 question is that what this string of ones and zeros actually mean. So the control unit need to decode it, and it need to decode it according to some predefined rules. And suppose the first 4 most significant bits represent the operation. I'm just assuming this 1, 0, 1, 1. These 4 bits actually represent the operation. Let's suppose, and further assume that this 1, 0, 1, 1 means addition. Okay, and we further assume that the remaining 12 bits, that is this 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, gives us the first operand for this add operation. And maybe it is the memory address where this first operand is located. Now, so these 4 bits means addition. These 12 bits may mean the actual data which needs to be added, and may mean the address in the memory where this data resides. Now, another $100 question is, what about the second operand, in which we need to add this operand? And yet another $100 question is, after doing the addition by the ALU, where we need to store the result. And yet another $100 question is, after we are done with this, what is the address of the next instruction to execute? Is it the next instruction in sequence, that is address number 2, or do we need to jump to some other address below over here? The answer to all these and many other questions is hidden in the instruction set architecture of this computer. And we will talk about this in detail in the next lecture, inshallah. But over here, let me touch upon some more important things that will help you to understand the next session. By now, we are quite sure that it is really difficult to understand what this series of zeros and ones actually mean. And if not impossible, it is really difficult to write down programs like a web server or a web browser or any other big application in machine language, and we need to write hundreds and thousands of instructions like these. And dear students, of course, no one do so these days. These days, programs are not written in machine language. So there is another option, and that is we devise a symbolic machine language having symbols instead of zeros and ones, and that language is called the assembly language. Let's suppose this is an assembly language instruction which says add R3 R2. So this instruction is comparatively easier to understand than this series of zeros and ones. So maybe these bits represent the operation. Over here it is, let's suppose, the add. These 4 bits represents one of the registers. Let's suppose this is R3, and these 4 bits represent another register. Let's suppose this is R2. So the instruction is add R3 R2. We may mean that add the contents of R3 and R2 and write the result in R3. But dear students, even if we have written a computer program in assembly language, we still need to convert the program written in this assembly to machine language before executing it actually on the computer hardware. And the program that do so, that is the program that converts this assembly language to this machine language, is called an assembler. And uh, there has to be somebody who is going to write this program for us. That is, there need to be someone who is going to write an assembler for us. Okay, so well, over here in the previous slide I have shown you an instruction that add the contents of 2 registers, and over here I am showing you an instruction that actually increments the contents of memory location. Suppose, so this is a machine language and this is the assembly language, hypothetical assembly language, which says add 1 to the memory address pointed to by this address mem129. But dear students, for a programmer, it is a bit difficult to specify and memorize the memory addresses for different purposes. A more friendlier syntax can be used if we assume that the symbol, let's suppose, index stands for this mem129, and the assembler will resolve the symbol index into specific memory address. So the assembly language will become more simpler to us, which will say add 1 comma index. Over here, this is a symbol which the assembler will automatically map to mem129. So for an assembly language programmer, it is a bit easy for him not to memorize the exact addresses. Dear students, we are of course going to design the machine as well as the assembly language for our hack computer in the later part of our course. But over here, I just want you to have a basic idea that there is something called a machine language, and there is something called assembly language, and there exists a program called assembler, which is capable of translating a assembly language program to the corresponding machine language. Uh, okay, fine. Although we will discuss in detail about the instruction set architecture in our next lecture, but let me give you an overview before we close today's session about the ISA. So dear students, every computer has an instruction set architecture, ISA, which is a set of instructions, registers, memory space, and other features visible to the assembly language programmer. You can say that it is an interface between the hardware and the low-level software, and sometimes referred to as machine language as well, although it is not entirely accurate. Anyway, so there are different ISAs, for example, x86, ARM, MIPS, PowerPC, SPARC, RISC-V. So x86 is the ISA for the x86 architecture used in the general purpose computers. ARM is generally used in the embedded systems. Anyway, so there are 6 different dimensions of ISA which I will be going in detail in the next session. Today I will just name them for you. The first is the class of ISA. Well, dear students, there are different classes of the instruction set architecture. The main 3 are the stack-based architecture, the single accumulator architecture, and the general purpose architecture. The second dimension is the types and size of operands. By that I mean what is the size of the operand that ISA support? Is it 16 bit, 32 bits, or 64 bit? And what are the types, like the support of characters, integers, or floats? The third dimension is the operation. By that I mean the different types of arithmetic and logic operations that are hardwired in that ISA. Uh, the fourth dimension is the memory addressing model and addressing modes. By memory addressing model, I mean what is the view of the memory layout for the assembly language programmer. And by addressing mode, I mean different ways in which the operands of an instruction can be specified. The next dimension of ISA is the control flow instruction, which means how does the uh, language allows us to decide and specify which instruction to process next, whether it is the next instruction in the sequence or it is a jump instruction. And finally, the encoding of the ISA. By encoding of ISA instruction, I mean how to encode all the above information in the 16 or 32-bit machine instruction. Well, dear students, this is just an overview, of course, and we will discuss all these six dimensions in detail in the next lecture, inshallah. And uh, in the later part of the course, of course, we are going to design this ISA for our hack computer. And by that time, I am sure that you will completely understand uh, these terms which might be quite Greek to you right now. Okay, so that is all for today's session. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.